Hi, I'm Macie Whatley, and this is my Lab 9. The problem and the result. The objective of this lab is to model an oscillating mass attached to a spring using the momentum and the energy principles. The main result was that using those principles, we were able to predict the motion of the oscillating mass. I verified that the sum of all the energies is equal to 0 from the data using the model. The model is relevant to the physical system, so this is just our initial conditions. I changed the ball mass to 0.402. The ball position is the initial position that I got from my tracker data. The ball velocity starts at 0 because it comes up from rust from Dr. Greco's hand. Ks you can find by doing 1 over t, the period, which is the time between two peaks and trackers. So you can just look at those 2 points and subtract. So mine was 1.52. So 1 over the period equals 1 over 2 pi times the square root of Ks over mass. So we can use that to solve for Ks, which gives us 6.869. Next, we can use that and find our rest length of the spring. We know that the stretched is 0.7, which was a static equilibrium. So we just solve that using our new Ks and get 0.125. The delta T is 1 over 210, and the total time is 9.212 seconds, which you can see down here. The correct position versus time. Now I'm going to show you my data, my Python when it's run. So here you can see that the two balls follow each other very closely. I sped it up just for the sake of time, but the accuracy nonetheless is still there. So here you can see the model matches what actually happened in the video. The blue ball is from Tracker and the orange ball is from Python, and they follow the same path very closely. That just shows that they're almost the same, which is or basically the same, just negligible difference, which indicates the accuracy. The graph that was to the right was the yellow line was the sum of the energy, the red line is the change of the energy, the green line is the change in kinetic energy, the blue line is the change in potential. We'll revisit this later in the what does it mean, but you can notice that the yellow line, which was the sum of all the energy, it was equal to 0, it just went along the axis, which is exactly what we wanted to see. Connecting the model to the data. So this is the calculations using the principles. So here you can see first we're going to calculate the force of gravity, which is just mass times gravity. That's what's acting in the y direction. Then this is in a loop, so what we're going to do every time is get that stretched value and get a new S from that, from our L naught that we're using, that's the constant, and then we calculate the force of the spring at that point. So it's going to go and update it every single time. And then we're going to do F net, which is just the gravitational force plus the spring force. The spring force is just the negative Ks, the spring constant, times that change of L to L naught, the S, times L hat just makes it a vector. Then we're going to update the velocity. The velocity is just the ball's velocity plus the force divided by the mass times the change in time. That's the momentum principle. The ball's position is just updated by doing ball position plus the velocity times the change in time. Down here you can see where we can calculated all of the different energies. Kinetic energy is just 1/2 mv squared, which you can see right there. Delta, the change is just take the old one minus the new one and you get the change. For potential, you see ball mass times the magnitude times the ball's position gives you that potential, which is just the gravitational. The magnitude is the magnitude of the g, the constant. So that gives you like the gravitational potential energy, which is what we have in our system. Work is just the dot product between the spring force and the ball's velocity times the change in time. Delta E is just delta kinetic, change in kinetic plus the change in potential minus the work. The parallel and perpendicular forces were calculated to find the momentum, which isn't actually relevant here. The change in the potential spring is just the negative work. So what does it mean? Compare the period of oscillation you found from examining the x component of the position with the period of oscillation determined from the y component of the position. Do they differ? For the y position, I got 1.52. For the x, I got 1.61. These numbers have a difference because if you think about it, there's a force acting on the y position that's not acting in the x position. That force is gravity, so that causes a difference. With your new choice of systems, determine the work done by the surroundings. Is the energy principle satisfied? The energy principle says that delta E equals 0. That is satisfied, and we could see that from our graph earlier that showed that the The sum of all the energies is equal to 0, with the yellow line just going along the axis, which means that there is no surrounding work, so W equals 0. When defining the gravitational potential energy, if you change the coordinate where it was located, would that change anything? The actual physics don't change in the system. The changes in the quantity of energy do occur. The potential energy will change due to the new position, but the potential energy has to do with interacting objects, which is why you get the change. But the change in the quantities of the energy are the same, which is why the plots look the same here. You can see this is with the axis at the attachment point, and this is at the equilibrium state. And they're the exact same because the changes are the same. Thank you for listening to my video. Hope you enjoyed.